Less than 4 generations ago, transportation was neither better nor faster than it was 4,000 years ago. The Conestoga wagon still was the last word when the winning of the West began. Industry was not much farther along than transportation. Men still had only primitive tools to make the weapons and implements they needed for the work of opening up a new continent. But civilization rolled west on such wheels as these, and crude as they were, the wheels were strong because craftsmen have always appreciated the need for accuracy. Blacksmith used what was called a traveler, one of the many forerunners of our accurate modern gauges. It helped him make the steel tire fit the wheel. But even with the help of the traveler, the job was a tough one. When we consider the slow hand methods by which the old Conestoga wagons were built, it is no surprise to learn they cost as much as a modern automobile, and time and the cost came from the fact that fitting parts together was largely a matter of cut and try. Measuring, sighting, and fitting often had to be done again and again before a satisfactory result was obtained. Uniform high quality and quantity production were both beyond the craftsman's reach. These achievements waited on modern science and industry. Out of research in industrial plants throughout America has come the knowledge to make better products at lower cost. This research work begins with the raw materials, which are required in enormous quantities. More effective ways to use them are being sought all the time. And while this search goes on, the equally important work of testing and retesting the raw materials is conducted endlessly. In making an automobile, there are many complex steps from the raw materials to the complete car. Some idea of this is gained by the fact there are approximately 15,000 parts in a Ford V8. Every single part must be made exactly right and out of exactly the right materials. Each must be made as accurately as if it were the only part turned out in the entire plant that day. Here, standard of quality for materials are established and safeguarded. And here research men try to find out all there is to be known about these materials and the parts made from them. For this, they use many ingenious research instruments. This upholstery, for example, wasn't chosen by guesswork. It will continue to look good for years. The research men know because they put samples of it and of dozens of other fabrics through tests that left no doubt about it. This device is called a phaedometer. It produces concentrated sunshine in the form of ultraviolet rays. If a fabric isn't color fast, it can't get by this test. But wearing qualities, just ask this boy's mother, are even more important. And so, upholstery fabrics are placed in this machine to get a real workout, because the machine never tires out. It gives the sample 6,000 of these scuffing, wearing strokes an hour under constant pressure until they finally wear through. Even the most active little boy couldn't match that. By this test, wide differences often are revealed in the durability of fabrics that look about the same. The same rustless steel that keeps this paring knife bright without polishing gives lasting beauty to the decorative trim of the modern motor car. Rustless steel is bright all the way through. But what of plated and enamel surfaces? If they're deeply scratched, will rust spread beneath the finish? The engineers wanted to know, and so they built this special salt spray room to find out. They gave the room, of course, a door of rustless steel. Here, warm salt spray, even more concentrated than along a windswept tropic seacoast, attacks various car parts in tests that last hundreds of hours. They must come shining through treatment much worse than they're likely to get in actual service. To run quietly and to keep on running quietly for years, the car's hundreds of moving parts must be smooth. But just how smooth is smooth? Velvet is smooth to the touch, so is glass. These plates, for example, look alike and feel alike, and formerly would have been regarded as identical. Actually, however, one is twice as smooth as the other. This machine tells us that. It is a profilograph, the first ever made for an automobile plant. University of Michigan scientists developed it to enable engineers to do something they never could do before. That is to find out just how smooth really is. They call these pictures profilograms. They show all the irregularities in the surface of the sample, magnified 1,700 times. You see here how much smoother one of the glass samples is than the other. For very close study, the profilogram, in this case, that of the piston pin, goes into this powerful microscopic projector. By use of this device, surface irregularities of only 1/1,000,000th of an inch may be measured on all finished surfaces. This information helps in making parts smooth, silent, and durable. The X-ray, as everyone knows, has given physicians a powerful new instrument in the diagnosis of human ills. The same instrument is almost as useful in industry. Let's watch an industrial X-ray photograph being made. Generated by the tube in this 230,000-volt X-ray machine are so powerful that the entire room is lined with lead, 8 tons of it, to keep the rays inside. As the operator turns on the power, the rays shoot through the crankshaft and photograph the internal structure of the metal. They can easily go through 4 inches of solid steel. Study of the X-ray photographs helps the engineers to know the exact possibilities of every one of the 63 different kinds of steel that goes into the making of these cars. This 200,000-pound compression and tension machine is putting enormous pressure on a single ring gear tooth to test its strength. It is a test worse than any the gear would get, even in the toughest kind of going. The pressure goes up and up to more than 35,000 pounds before suddenly the tooth gives way. As easily as this housewife wrings out a dish towel, this machine twists up a front axle. The axle, which is made of heat-treated manganese alloy steel, is twisted around and around again for 9 complete turns without a break. This is proof, and impressive proof, of the toughness of this vital part. Because they have stronger, tougher, and more uniform steel to work with, the engineers make car parts stronger and much lighter than was possible a few years ago. This strength enables the parts to carry great loads and to withstand the countless little bends or deflections that would tire out metals of poorer quality. Everyone who remembers breaking a wire, as this boy is doing, knows the principle of fatigue in metal. The materials in cars and trucks are designed to resist fatigue for the entire life of the vehicle. The extra margin of fatigue strength is accurately measured in frequent tests. This tester has been called 1,000,000 miles of rough road in a 10-foot box. By breaking down parts on it, the engineers help prevent breakdowns on the road. Iron and steel, of course, are the foundation of modern industry. And in the last 35 years, more ways to increase the usefulness of these metals have been developed than were found in all the centuries before. Much of this progress is the result of using other metals as alloys in iron and steel. To produce just the kind of metal needed, the metallurgists must control these alloys very carefully. Ford metallurgists have a remarkable method for doing this. They analyze each batch of metal before it is poured. This is about the same on a grand scale as for a housewife to make certain the soup has just the right taste before it is served. This is possible because every metal, under certain conditions, has a rainbow of its own. That is the basis of this newly developed method for analyzing materials. They've put the rainbow to work. Here's how it works. A sample of the molten metal is drawn out of the furnace and poured in a special casting box. The casting is cooled, then placed in a container and sped 1,600 feet through this pneumatic tube from the foundry to the spectrographic laboratory. The steel sample is polished and placed in this 40,000-volt spark gap. The light from the spark goes through this tube to the spectrograph and camera in the adjoining darkroom. The light is broken up into rainbows by this spectrograph, and the lines each metal forms are photographed. The rainbows look like this when their pictures are taken, but those little lines tell the metallurgists a big story. Each of the lines means something. In this instrument, they're examined and their density noted. By accurately measuring the density of the lines, the exact amount of the metal in the alloy is determined. Just 8 minutes from the time the sample is received, a report on it is back in the foundry. The report may call for the addition of some element needed to keep the proportions of each metal in the alloy correct. This saving of time ensures quality. In addition to the big main laboratories, there are a dozen smaller laboratories scattered through the plant. The big labs establish the standards of quality, but these standards aren't left to enforce themselves. They're carried out by men in these special laboratories located right where the glass or steel or tires are being made. The workout junior here is giving this teething ring is, as you see, child's play compared with the systematic tests given samples of the 200 rubber parts that go into each car. On test are fan belts, tires, tubing, and body mountings. All vital engine parts, not just occasional samples, but all of them, are gauged in rooms like these, near the point of production. The gauges are very accurate, and to make certain they stay that way, the rooms are air-conditioned. Otherwise, changes in temperature might affect their precision. Ford gauges take many forms, and some are very ingenious mechanisms. For example, this piston pin inspection machine, developed and built by the Henry Ford Trade School, is sensitive to differences as little as 25 millionths of an inch. It automatically gauges and sorts 2,250 piston pins per hour. This machine also checks each pin for hardness, roundness, length, finish, absence of taper, and diameter, then sorts the pins into a 5-compartment container according to size. Without this machine, it would not be practicable to examine every piston pin with such care. Timing of amazing accuracy and grace makes this circus act an outstanding success with the crowds. Precise timing is of top importance in an engine, too. And for that reason, camshafts must be made just right. This camshaft inspection machine, also designed and built in the plant, checks every measurement on every camshaft automatically. On the high wire, balance of the most delicate kind is needed, and these star performers have what it takes as they go through their daring routine. Balance is also one of the prime factors in a crankshaft. In this room, crankshafts are checked for both static and dynamic balance on these machines. Even the weight of a thin dime would throw the crankshaft out of balance. To ensure that every valve seat insert is perfect, all of them are subjected to an unusual test. A good ping pong ball bounces well, but a bad one won't. So it's easy to find and throw out the bad ones. Much the same method is used in testing valve seat inserts in this machine. Perfect rings bounce into the container, but those not up to specifications for hardness and solidity can't bounce high enough, and so fall into the container for rejected rings. The machine also discards odd-sized rings. More than 38,000 precision gauges are in regular use in the production departments of the Rouge plant. Many of them are accurate to within 1/10,000th of an inch. To make sure that they stay accurate on the job, they're checked with Master Johansson gauge blocks. These blocks are recognized as the world's standard of measurement. Production gauges, the gauges employed right in the shop, are checked against them at least once a day. Tested materials. But Ford testing methods go beyond tests of materials and parts. At regular intervals, a car is taken off the production lines to go to destruction for the sake of science. For these doomed cars, there's a whole series of tests on the test tracks and in the new weather tunnel. A car is driven into the tunnel where weather equal to the world's worst of Arctic tundra and tropic desert, of mountaintop and seacoast, is made to order. The car goes on a treadmill, and the man at the control speeds up the engine until the rear wheels are spinning near top speed. Then he opens the sleet-making mechanism and turns on the big propeller. The temperature drops to 0, and ice quickly coats the car, while the wind velocity rises to 70 miles an hour. What a storm this is, and what a test of car stamina. For hour after hour, the car runs on, while engineers tabulate the data brought them by nearly 100 recording instruments. Then the temperature may be sent abruptly upward. Instead of an Arctic storm, Suddenly, we have the scorching heat of the Sahara in summer. Humidity goes down. The load of the treadmill is increased to imitate the dragging action of deep desert sand. Still, the car rolls on. Then, without moving an inch, the car is transported from desert to mountaintop. How? By reducing the air pressure until it duplicates the rarefied atmospheric condition of a lofty peak. Still another turn of the controls, and dust and sandstorms may be hurled in turn against the car before it is drenched in torrential tropical rains such as we see. In short, almost every conceivable type of weather can be produced in this tunnel. The purpose, of course, is to find out promptly how newly designed cars will perform under every condition. To find out now without being obliged to wait for reports from test cars in remote parts of the world. And now for an idea of what all this varied research means to the car owner. For many hours, this car stood in the tunnel in a temperature of 20 degrees below zero. But it starts almost instantly and is backed out of the tunnel. Without a moment for this chilled mechanism to adjust itself to the abrupt change, it is driven onto the test track. It never falters, never misses fire, as the driver, peering out of the tiny cleared patch on the windshield, speeds around the track. The tunnel also is valuable for research in body design. Cars are suspended in aerodynamic balance and tested in an air stream from the big three-bladed propeller to discover the amount of air resistance, or drag, they present at various speeds. These tests also show the gain in slipstream efficiency, made possible by changes in the contour of bodies and body fittings. This data helps the designers make cars that are more efficient and more economical. In addition to tests of the performance of the entire car, the efficiency of batteries, radiators, insulation, and other factors is tested in a special cold chamber where the temperature may be sent down to 40 degrees below zero. Dressed like a polar explorer, the research man goes steadily forward with his experiments, telephoning the results of each to his colleagues stationed outside the observation window. Restful quiet in a car, even if it is traveling fast over brick roads, is one of the things demanded of the modern automobile. Some clever equipment was developed to let the engineers find out just what makes sounds, how they get into the car, and how to damp them out or silence them altogether. Road tests, in which sounds are measured at all speeds from 20 to 70 miles per hour, are conducted over many different kinds of road surfaces. Engineers equipped with sound level meter, stethoscope, microphones, vibration analyzer, and other special instruments trace down all disturbing noises. Sometimes the word hunting noises leads to unexpected places, such as the luggage compartment. Armed with accurate information, the designers develop car bodies that bring a new quietness to motoring. Cars are tested on this track. The high-speed section, the gravel, cobblestone, Belgian block, and other sections provide information, performance, and safety factors in the cars. The tests go on all the time, day and night, summer and winter. By far, the most formidable part of the test track is the torture section, a 1/3 mile stretch of concrete mounds in a staggered double line. One test of the springs and shock absorbers requires the car to be driven over a single row of mounds in a terrific bouncing action. And then, with the car traveling at 40 miles an hour down the center, comes another test just as bad. If there is any possibility of any part of the frame or any of the body mountings working loose in thousands of miles of normal service, the engineers find it right here. Science in the automobile industry advances on a score of fronts. The tests and research methods of the Ford Motor Company, which we have just seen, are only a few of the more outstanding developments which have helped make the American motor car a worldwide symbol of efficiency and value. Seeing them, however, may help bring a wider realization of to bring greater safety, value, and